Sankara Education Institution is founded with a motto to serve the students' community by providing world-class education and over 30 years of academic excellence. We cater to the needs of diverse categories of people who aspire to pursue their UG degree, PG degree, MBA, MPhil degree and diploma in engineering. Sprawled in 40 acres of lush green and eco-friendly campus, Sankara provides a fresh and calm ambience for students. Sankara Educational Institutions is equipped with modern infrastructure and state-of-the-art facilities adhering to international standards. Students never miss the classes because learning at Sankara is practical, productive and fun-filled.
At Sankara, every student will learn, achieve and succeed.
Chapter 2 Current Electricity. In this chapter, we will be dealing with charges at motion. So, current electricity is the branch of physics that deals with the study of motion of electric charges. Let us consider the atom of an uncharged metallic conductor. Let this be the nucleus and let there be electrons revolving around the nucleus. There are electrons. In a conductor, not all the electrons are bound tightly to the nucleus. Some electrons, due to thermodynamic internal energy of the atom, may get knocked out. So, because of the internal energy, some electrons, let us say this electron, they may get knocked out and they are free to move within the conductor. So, if this is the conductor, let this be the atom. Because of the thermodynamic internal energy, the electrons here might get bumped out. So, electrons will be released into the material and the atom becomes a positive ion. So, the atom now becomes positive ion. And these free electrons are free to move in any direction. They won't be flowing in a particular direction. When it is uncharged, it is free to move in any direction. So, the electron may move in this direction, this direction, this direction, or in this direction. But the net flow of charge at any point is 0. What does it mean? Let us say the free electron, let us say there is one free electron which is moving in a particular direction. This free electron in the conductor may collide with another free electron or with an ion, the ion that is created. So let us say it is colliding with another electron. So when this happens, this electron will be bounced back with the same speed. So the speed before collision is equal to speed after collision. This will be the case with all the randomly moving free electrons, and hence the net flow of charge at any point is 0 because the electron that is moving in one direction comes back after bouncing with another electron. So the net flow of charge at any point is 0. Hence, in an uncharged metallic conductor, since the net flow of charge is 0, at any point, the net current is also 0 in a uncharged conductor. Uncharged conductor is an important 1 mark question. How do we make these free electrons to move in a definite direction. For that we need to apply some potential. What is the potential? The potential is the work done in moving a electron or a charge from one point to another. This external energy that is necessary to drive the free electrons in a definite direction is called electromotive force. Electromotive force or simply EMF. So consider a metallic conductor. Let it be connected to a potential, and when the metallic conductor is uncharged, the electrons will be moving in random direction. So E minus in this direction. But when a potential is applied, let's say this is the positive and this is the negative side. So when a potential is applied, the free electrons which are moving randomly in any direction will start to flow in a definite direction. So this will be the direction of the flow of free electrons. There is a potential that is connected. So this is the net direction of flow of the electrons. When this happens, it constitutes electric current. Definition of electric current. It is defined as the rate of flow of charges. Rate of flow of charges is nothing but charge per unit time, or simply Q by T. So electric current is defined as the rate of flow of charges across any cross-sectional area of a conductor. It is expressed by the symbol I and its unit is ampere. So current I is equal to Q by T ampere, where Q is the charge flowing and T is the time in seconds. So Q represented Q in coulomb and T in seconds. And in most times the rate of flow of charge is not uniform. That is, the charge Q flowing through the conductor per unit time is not uniform, which will result in the current I varying with time. So if this happens, current also varies with time. This instantaneous value of current is given by I is equal to dq by dt, where I is equal to instantaneous current and dq is change in charge, dt is change in time. Current is a scalar quantity. Drift velocity and mobility. Drift velocity and mobility. Let us consider a metallic conductor XY. When it is uncharged, the electrons are free to move in any direction. We saw this before. The free electrons will move in random directions in an uncharged metallic conductor. Now what happens to this electron when it is connected to a potential or a battery? So when a potential is applied, let this be the positive and let this be negative, let this be positive and let this be negative, an electric field will be generated. Electric field will be in the direction of the potential. So this is the direction of the electric field, and when an electric field is applied, the free electrons, this one will experience a force F is equal to EE. So the electron will experience a force F is equal to EE in a direction that is opposite to the electric field. Why is that? Because this electron, which is a negatively charged particle, negative electron, will be repelled by the negative terminal. We know that like charges repel, so the electron, which is a negatively charged particle, will be repelled by the negative terminal and it will be attracted by the positive terminal. So the electron will start to move in this direction with the force F is equal to EE, which is in a direction that is opposite to the electric field. So this is the initial velocity of the electron V. Now similar to the electrons, the positive ions will be repelled by the positive terminal and attracted by the negative terminal, and they will start to move in this direction, isn't it? Because like charges repel and unlike charges attract. So the positive ion will be repelled by the positive terminal and attracted towards the negative terminal. So when this happens, there are chances that the positive ion and the negatively charged electron will collide with each other. Sometimes the electron might collide with another electron as well. So when that collision happens, the electron that is moving in a specific direction will experience a backward force because of the collision. What happens when two balls collide? The balls will bounce back with certain force. That is what is happening here also. So the electrons will bounce back with a certain backward force, but the net potential that is applied at the ends of the conductor will still make the electron to move towards the positive terminal, but the movement will be restricted by the backward force to some extent. So although the electron is still moving towards the positive terminal, there is a small backward force that is acting on it. So this velocity with which the electron is moving towards the positive terminal is called drift velocity. So a drift is nothing but a slow movement of a particle from one place to another, and this slow movement is caused by the backward force developed due to collision with other ions or other electrons. So this is drift velocity. So the definition is, drift velocity is defined as the velocity with which free electrons get drifted towards the positive terminal when an electric field is applied. Conventionally, the direction of current I is along the direction of the flow of positive charges, which is in this direction. Or from the diagram we can also say that the direction of the current is opposite to the direction of the flow of electrons. So this is the direction of flow of electrons. So current will be in a direction opposite to the direction of flow of electrons. Now we also know that force can be represented as mass into acceleration. Here mass of electron into acceleration of the electron, and acceleration is defined as velocity by time. So let tau be the average time between two successive collisions. As we told, the electrons will collide with other ions or free electrons, and tau be that average time between two successive collisions. So this equation can be rewritten as velocity is equal to acceleration into time, or Vd, which is drift velocity, is equal to acceleration into tau, which is the average time between two successive collisions. Let this be 1, let this be 2, let this be 3. 2 can be rewritten as F is equal to ma, or A is equal to F by m, and this equation can again be rewritten as A is equal to E by m. This is from 1. Now 3 can be written as Vd is equal to A into tau. We know the value of A, which is equal to E by m into tau. Or rewriting this, Vd is equal to, bringing all the constants together, E tau by m into electric field. This value is represented as mu, which is a constant, and it is called mobility. So Vd is equal to mobility into E, where mu is mobility. Mobility is defined as the drift velocity acquired per unit electric field. So mu is equal to Vd by E. So it is defined as drift velocity acquired per unit electric field. So what is the unit of this mobility? Let us derive it now. Drift velocity Vd. What is the unit of velocity? Meter per second divided by what is the unit of electric field intensity? It is nothing but volt per meter. So when this meter moves up, it becomes meter square, meter into meter per second per volt. The volt in the denominator, when you have to represent it, becomes per volt. So unit of mobility is meter square per second per volt. Also from this equation we can say that drift velocity is proportional to electric field intensity. The value of drift velocity is very small because it is the movement of electron with a backward force on it due to collision. So that is called drift. Drift is nothing but slow movement of a particle from one place to another. So the value of drift velocity is usually very small and of the order 0.1 centimeter per second. Current density. Earlier we have defined current. Current is the rate of flow of charges through any cross-sectional area of the conductor. It is the rate of flow of charges. When current is divided by area, which is Q by T, the whole divided by A, it becomes current density, which is denoted by the symbol J. So current density is defined as the rate of flow of charges per unit area, or the number of charges flowing per unit time. The number of charges flowing per unit time per unit area is defined as current density. The current density is taken perpendicular to the direction of flow of charges at that particular point, and it can also be written as Q by T is I by A. J is equal to I by A. And let us derive its units. We know the unit for current is ampere and the unit for area is meter square. So current density's unit of J is ampere per meter square. Current density is a vector quantity. It is a vector quantity and is taken perpendicular to the direction of flow of charges at that point. Now let us derive the relationship between current and drift velocity. Relation between current and drift velocity Vd. Let us take the same example. Let this be the conductor XY and connected to a battery or potential plus minus plus minus. So the number of free electrons in the conductor, let these be the free electrons, and when a potential is applied, an electric field is generated, and as we discussed before, the electrons will start to move from Y to X with a drift velocity Vd. So N be the number of free electrons or number of conduction electrons per unit volume. Which is nothing but N is equal to number of electrons per unit volume. So what is the total number of electrons in the conductor? Total number of electrons in the conductor is equal to number of electrons per unit volume into total volume of the conductor, which can be rewritten as number of free electrons into volume is area into length. So let A be the area, cross-sectional area of the conductor, and L be the total length of the conductor. Let this be L. So this is the total length of the conductor. So the total number of free electrons in the conductor is equal to N into AL. Now we need to find out the total charge Q passing through the conductor when the potential is applied. We know the formula for finding Q. Q is equal to N into E, the integral multiple of fundamental unit of the system. So N into E. N is nothing but the total number of electrons, which is represented by NAL. So N into A into L into E is nothing but the charge of the electron. So NALE. So this is the total charge passing through the conductor. Now we need to mention velocity. What is velocity? Velocity is distance by time. Distance by time. So drift velocity Vd is, distance is the length of the conductor L by time is t. From here t can be written as t is equal to L by Vd. So we have Q, we have t. Now what is the current flowing through the conductor? It is Q by t. You have seen this before. So substituting Q and t, NAEL divided by L by Vd. So L gets cancelled out and Vd will go to the numerator. So I becomes NAEVD. Let this be equation number 1. And number of free electrons in the conductor, area and the charge of the conductor are constant. So we can give a single constant. So we can introduce the proportionality symbol here. I is proportional to Vd, which is nothing but the current flowing through a conductor is directly proportional to the drift velocity. So this is an important one mark question. Also from equation 1, we can derive the current density formula. In equation 1, I is equal to NAEVD. Bring A to the denominator. So I by A is equal to NEVD. We know I by A, which is nothing but current density. J is equal to NEVD. So this is the relationship between current density and drift velocity, and this is the relationship between current and drift velocity. Ohm's law. A scientist named George Simon Ohm, he established the relationship between the two important quantities of current electricity, which are potential and current. He told that potential is directly proportional to current. This came to be known as Ohm's law. Let us consider the example. Let XY be the metallic conductor connected to a potential. So when a potential is applied, charges will start to flow. They flow from X to Y in the metallic conductor. What happens when you increase the potential? More charges will start to flow, which means more current. Correct? When you increase the potential in the battery, more charges will start to flow from X to Y in the metallic conductor, which means there is more current. This is how this relationship between potential and current was derived. Let us see the derivation now. The current flowing through the conductor I is NAEVD, velocity, drift velocity. We also know that Vd is nothing but E by m into tau. Substituting Vd in 1. Substituting Vd in 1, I is equal to NAE E by m into tau. which is equal to Na E square E by M into tau. We know that E can be written as V by L, which is potential gradient. So I can be rewritten as Na E square, replacing E with V by L into tau by M. Bringing all the constants together in the above equation, I is equal to Na E square tau by Lm into V, where N is the number of conduction electrons, A is the area of the conductor, cross-sectional area of the conductor, E is the charge of the electron, tau is the time between two successive collisions, L is the length of the conductor, M is the mass of the electron, and V is the potential applied to the conductor. So this is a constant. Rewriting this equation, I can be written as I is equal to V by, taking reciprocal of this constant, L M by Na E square into tau. So the constant can be represented by the letter R. So I is equal to V by R, where R is the electrical resistance, or simply resistance of the conductor. Resistance of the conductor. Or the above equation can be written as V is equal to R into I, taking R to the numerator of the left hand side. Introducing proportionality, V is proportional to I. So this is the Ohm's law. So let's talk about this resistance now. From equation 1, we can rewrite resistance as R is equal to V by I. So resistance of a conductor is defined as the ratio of potential difference across the conductor to the current flowing through the conductor. So R is equal to potential difference developed across the conductor by the current flowing through it. The unit of resistance is given by ohm, or represented by the symbol, this is ohm. The reciprocal of this resistance, which is 1 by R, can also be called as conductance. The unit of conductance is the reciprocal of ohm, or simply mho, or ohm inverse. A graph between V and I with V along x-axis and I along y-axis will give a straight line, which means as V increases, I increases as well. Ohm's law holds good only when a steady current passes through the conductor. Now let us discuss a little more about resistance. Can be considered in general as an opposing property or a resisting property. Opposing property to the flow of current. Opposing property to I. Why is there a resistance developed in the conductor? We have discussed before that whenever a potential is applied, the free electrons will start to move in a definite direction, and while they are moving, they might collide against the positive ion or another free electron. So when it collides, there will be a backward force developed, due to which the drift velocity comes into existence. Because of this collision, resistance developed against the flow of current. So in an ideal situation, in a conductor connected to a potential, when an electric field is applied, electrons will start to flow in this direction. As a result, current will flow in this direction. The direction of current is opposite to the direction of flow of electrons. So current will start to flow in this direction. And when there are no collisions between the electrons and the positive ions, or between the electrons and other electrons, there won't be any opposing force, and the potential applied is directly proportional to I, which means there won't be any loss, or there won't be any opposing force to the current. But in the actual case, these electrons will collide against the positive ions that are moving in the opposite direction, or may even collide against the other free electrons that are moving in this direction with varying velocity. Because of that, a backward force is developed which resist the movement of this electron towards the positive potential, which we call it as resistance. This is how a resistance is developed in a conductor when you apply a electric field. We found out that resistance is given by the formula Lm by Na E square into tau. From this equation, let it be equation 1, we can see that resistance is directly proportional to the length of the conductor and inversely proportional to the area of the conductor or the cross sectional area of the conductor. So here the mass of the electron is constant, number of free flowing electrons is a constant, E square, which is charge of the electron, is a constant, and the collision between two electrons or the time interval between two successive collisions is also a constant. In such a case, resistance can be considered proportional to the length of the conductor and inversely proportional to the cross sectional area of the conductor. So these two equations can be combined to give R is directly proportional to L by A. This is the length of the conductor and the cross sectional area be A. Now to remove the proportionality symbol, we are introducing a constant. R is equal to rho L by A, where rho is the specific resistance or electrical resistivity of the material. Resistivity of the material of the conductor. So the resistivity can be written as rho is equal to, from this equation, R A by L, and the unit of resistivity is, we know the unit of resistance, which is ohm, area is meter square by length is meter, so meter and meter gets cancelled, so unit of resistivity is ohm meter. Now let us consider a metallic conductor of length L is equal to 1 meter and cross sectional area A is equal to 1 meter square. So in this case, the resistivity is given by R into A is 1 meter and L is 1 meter. So resistivity is equal to R. So now we can define the electrical resistance of a resistivity, the electrical resistivity of a material, as the resistance offered to the current flow by a conductor of unit length with a unit cross sectional area. The electrical resistivity of a material is defined as the resistance offered to the current flow of a conductor of unit length having unit cross sectional area. This electrical resistivity is constant for a particular material. So no matter how large or what is the cross sectional area of the material, rho is going to be constant for a specific material. The reciprocal of electrical resistivity is nothing but electrical conductivity, which is represented by the symbol sigma. So what is the unit of sigma? Unit of sigma is 1 by rho. We know the unit of rho, which is 1 by ohm meter, or unit of sigma can also be written as ohm inverse meter inverse. Classification of materials on the basis of resistivity. Classification of materials based on resistivity. We know that materials can be classified into conductors and insulators. Conductors, as the name suggests, conduct electricity, which means they will allow current to pass through them, or the charges to pass through them freely. So in conductors, the resistivity will be low. So resistivity will be low in conductors, and the resistivity value will be of the order 10 to the power minus 6 to 10 to the power minus 8 ohm meter, thereby making the materials good conductors of electricity since the resistivity is low and the resistivity value is of a very low order, 10 to the power minus 6 to 10 to the power minus 8 ohm meter. Now, what happens when you increase the temperature of the conductor? When you increase the temperature of the conductors, resistivity will also increase. Examples of conductors: silver, aluminium, copper, iron, tungsten, nichrome, manganese, constantan. Now let us discuss about insulators. Insulators do not conduct electricity, which means they do not allow charges to pass through them or flow through them. So they offer very high resistance to the flow of current. So insulators offer very high resistance to the flow of current, which means the resistivity, electrical resistivity is high in insulators. And the value of resistivity for insulators will be of very high order, 10 to the power 8 to 10 to the power 14 ohm meter. Compare the difference here, it is 10 to the power minus 6 to 10 to the power minus 8. Very negligible resistivity. Whereas in insulators, it is 10 to the power 8 to 10 to the power 14, which is very high, which means there will be resistance to the flow of charges in these materials. When you increase the temperature in insulators, the resistivity will decrease. Examples of insulator: glass, mica, amber, quartz, wood, Teflon, bakelite. There is another type of material that falls in between conductor and insulator. We call them semiconductors. As per its word, it is semiconductor, which means it partially conducts charges or electricity, or these materials will allow few charges to pass through them. Conductors allow most or all charges to pass through them, whereas insulators give very high resistance to flow of charges, whereas semiconductors allow few charges to pass through them. The resistivity of the semiconductor is of the value 10 to the power minus 2 to 10 to the power 4 ohm meter. So this value lies in between these two values. Example: germanium, silicon. So this is the classification of materials based on resistivity.